You ever just look at your phone, your computer, or even just a simple flashlight and wonder, what is actually going on inside? How does this little box of stuff actually work? It can seem impossibly complicated, right? But what if I told you it all boils down to three really simple rules? Okay, let's get into it.
So take a look at this. This is basically a map of the entire world of electronics, and it comes straight from the book Practical Electronics for Inventors. And yeah, it looks pretty intimidating. You've got theory, all these different components, circuits. It's a lot, and it's easy to see this and just think, nope, too much for me. But here's the secret. All of that crazy complexity you just saw, it's all built on a foundation of just three core ideas. Seriously, if you can wrap your head around these three concepts, you'll understand the fundamentals of pretty much every electronic device you own. So let's break them down. Let's start with part one, the push. For anything to happen in electronics, you need some kind of force to get things started, right? Some kind of motivation to get everything moving. It's the energy that kicks the whole thing off. And that push usually comes from a power source, like a battery. Now, a great way to think about this is with a water analogy. A battery is kind of like a water pump. The pump doesn't create new water, right? It just creates pressure to push the water that's already sitting in the pipes. Well, a battery does the exact same thing. It doesn't create electricity, it just provides the push.
And that electrical pressure, it has an official name, voltage, and we measure it in volts. You can think of it like stored up energy, just a force waiting to be released to shove electric charge through a circuit. The main thing to remember is super simple. Higher voltage means a stronger push.
And this picture illustrates it perfectly. Look on the right. The deeper the water, the higher the pressure, and so the water squirts out farther. Now look at the left. It's the exact same concept. When you stack more batteries, you increase the total voltage, the total push, and that makes the lamp burn brighter. More pressure equals more power. Simple as that.
Okay, so we've got our push, which is voltage. So the logical next question for part two is, well, what happens when you push? You get movement. You get the flow.
And this flow of electric charge is what we call current, and we measure it in amps. Let's go back to our trusty water analogy for a second. If voltage is the water pressure, then current is how much water is flowing past a certain point every second. It's the rate of the electrical flow. Now, a quick but really important heads up here, and this comes straight from the book. These water analogies are fantastic for getting the basic ideas down, but, and this is a big but, electricity is its own unique animal. So use the analogy to build your understanding, but just remember it's a simplified model, not the whole story.
Okay, so we have a push, voltage, which creates a flow, current. But an uncontrolled flow can be a huge problem. It can even be dangerous. Too much water pressure can burst a pipe, and too much current can totally fry a sensitive electronic part. So for part three, we need to find a way to tame that flow. We need control. Think about it like this. A little LED light is tiny. A 9-volt battery is pretty powerful for that little thing. So what happens if you just connect them directly? Poof, you get a super bright flash for about a millisecond, and then that LED is toast. Forever. Why? Way too much current. So how do we fix that? The solution is this awesome little component, a resistor. You can see it right there in the diagrams. Without it, the LED burns out. But when you add it into the circuit, it does exactly what its name says. It resists the flow of current. It's like a valve in a water pipe, slowing things down to a manageable level and protecting that delicate little LED from the battery's full power. And that property of opposition is called resistance, measured in ohms. Honestly, you can just think of it as electrical friction. This is the control piece of our puzzle. It's a thing that limits the current to a safe and useful level. And while everything has a little bit of natural resistance, we use these things called resistors to control the flow precisely.
And as you can see, resistors come in all shapes and sizes. You'll find these teeny tiny ones on a computer motherboard, and then these big, chunky ceramic ones in high-powered equipment. But even though they look different, they all do the exact same fundamental job: control the flow of current.
So there we have it, our three key ideas: the push, the flow, and the control. Now, for our grand finale, let's put it all together and see how they combine to create the most basic thing in all of electronics: the simple circuit. So let's do a super quick recap to lock this in. The push is voltage, that's our water pressure. The flow is current, that's our water flow rate. And the control is resistance. That's the narrowness of the pipe slowing things down. Push, flow, control. If you get these three, you've got the foundation of all electronics down. Let's walk through it. Step one, the battery provides the voltage, our push.
Step 2, that voltage causes current to start flowing. Step 3, the resistor steps in and provides our control, limiting that current. And finally, step 4, that perfectly controlled current powers our device, which we call the load. In this case, the load is our LED, but it could be a motor, a speaker, anything. And this relationship isn't random. It's all governed by the most fundamental rule in electronics, Ohm's law. It's just a simple formula, V equals I times R. That means the voltage is equal to the current multiplied by the resistance. With that one rule, you can calculate and predict exactly what's going to happen in a simple circuit.
And here is how engineers draw it out. This is called a schematic diagram. It might look a little complicated, but you actually know all the parts now. See the 24V source? That's our push, the V. See those little zigzag symbols for the resistors? That's our control, the R. And the math, using Ohm's law, shows us the result, a perfectly controlled flow, our I, of 1.33 milliamps. It's the same three rules and that one formula, just written in the universal language of electronics. And that's really it. Voltage, current, and resistance. The push, the flow, and the control. From the simplest flashlight to the most complex supercomputer, these three fundamental principles are always at play. The magic inside your gadgets? It's not magic at all. It's just these three simple rules, applied in incredibly clever ways. So the next time you power on your phone or flip a light switch, you'll know the secret behind it all. You understand the basic rules of the game. So the only question left is, now that you know them, what could you invent?